Good morning, grade 12s. Welcome to Monday's lesson, Monday, May the what is the date today? May the 25th, sounds right. And we want to move into the last section of this unit, which has to do with electromagnetic induction, which will eventually, throughout the week, get us to how do we get electric energy from where it's generated to where we need it in an efficient and cost-effective manner. Before we get there, let's start with our verse of the day today. It comes from Psalm 62, and I'm going to read you the first two verses, but I encourage you to spend some time today and read all of Psalm 62. It is not that long. It is only 12 verses long, but there's some really good nuggets in there. So the first two verses of Psalm 62 say, "My soul finds rest in God alone. My salvation comes from him. He alone is my rock and my salvation. He is my fortress. I will never be shaken." So, good reminder as you go through the day today. And again, if you have time today, I encourage you to read all of Psalm 62 and be encouraged by what it has to say there. All right, electromagnetic induction. Now, before we get too far into this, we have to remember a few things from last year. And in talking to my own son about what he remembered from last year, it was not very much. So hopefully you remember something, but we'll go over a quick little review. So last year, you did a unit on electric charges, electric force, electric field and field strength and those kinds of things. And then you brought in magnetism and you did magnetic fields. And you should have learned some right-hand rules. And it's the right-hand rules that are a little bit important as we move into this year, because the right-hand rules give us direction. Okay, they tell us what direction a force will be applied on charged particles that are moving. And electricity, current, is simply electrons, charged particles, moving. And so when you have moving charged particles, they create a magnetic field. And when we have a magnetic field from that interacting with a magnetic field from a magnet, we get forces that happen. And from those forces and some of these properties, we can induce current. Now, inducing current simply means creating current in a circuit by using something else indirectly, right? When we induce something, it's not a direct thing. So all we've been doing so far is we've had a battery or a source of electricity and we've been running the circuit. Well, now how do we create a current in a circuit indirectly, okay, inducing it? All right, so first thing again, just remember, moving electric charges produce a magnetic field. So that's key. Anytime we have a moving electric charge, so current is moving electrons, we produce a magnetic field. And we had three right-hand rules, but only one of them is actually, well, two of them later on, but one is important for right now in terms of getting us going in this. And it requires you to remember what a solenoid is. So again, I don't know whether you remember this or not, but a solenoid is simply a coil of wires. And so I've drawn it here, and this rod in the middle, this tube in the middle, is simply just there to show that this wire is wrapped around it, okay, creating a coil, a loop of wires, okay? And the properties hold whether it's wrapped around something like this or not. We're going to move into Faraday's ring in a moment on the other board, which gets us into transformers, and there we do have wire coiled around a soft iron core, something that can be magnetized, right? And you know from previous experience that you can temporarily magnetize things, right? You've all probably magnetized paper clips or nails or those kinds of things in the past in some lower level science courses. Even if you go to some restaurants, sometimes there's a magnetic charge between some of the cutlery, you can attract things like that. So pieces of metal can be types of metal can be temporarily magnetized. And so when we have a solenoid, which is a coil of wire, and here I've got the current going up and around the back, and so we have a magnetic field being produced here because we have moving charge through it. And when we have a solenoid, the magnetic field of a solenoid looks very much like a magnetic field of a bar magnet. I don't know whether you remember what a bar magnet looks like, but a bar magnet has a north pole and a south pole, and then the magnetic field surrounds it in an oval shape. And so the same thing happens here. If I were to draw the magnetic field here, we would get something that looked like this, okay, which is similar to a bar magnet's magnetic field. Now, a bar magnet has a north and a south pole, and so does the magnetic field of a solenoid. It also has a north and a south pole, and that north and south pole is determined by the direction of the current and the use of a right-hand rule. And the right-hand rule is just a shortcut way of knowing which way, but the north and south pole is determined by the direction of the current. So, to find the north pole in a solenoid, you take your right hand, and you put your fingers, you wrap your fingers in a circle in the direction that the current is wrapping around the solenoid. So in this case, if this was my core, my right hand, my fingers are going to go in behind it first and then wrap around to the front. Like that's what this wire is doing. It's going in behind the core and then wrapping around the front. So if my fingers doing that, my thumb points to the north pole. So that would mean the north pole is at this end, meaning the south pole is at this end. All right, and so that's something to remember as we move into this, because again, with induced current, direction is important. Okay, I think you've all probably heard the terms alternating current and direct current, AC and DC, and we're getting into alternating current, and alternating means that the direction of the current is changing. All right, so a scientist by the name of Michael Faraday in the 1800s was the guy that was studying this extensively, and so he was taking wires, current-carrying conductors and magnets, and experimenting with them. And so he did a few different things. He would take a wire and he would move it through the jaws of a horseshoe magnet. So remember what a horseshoe magnet looks like? It's got the north and the south prongs, and he would take a wire, not a current-carrying wire, just a wire, and he would move it in and out of the magnetic field. And what he found with that was that the electrons would flow through the wire. He could create current in the wire, but only while the conductor was moving in the magnetic field. So if he moved it down, the current would flow. If he moved it up through the magnetic field, the current would flow. If he stopped in there at any point, the current would stop as well. Okay, and so and then he did a few other experiments. He took a bar magnet and a solenoid, and he would move this bar magnet in and out of the solenoid. And again, he found there that he could induce current in the wire, in the solenoid, while the bar magnet was moving. Okay, so again, while it moved in, it would create current. When he pulled it out, it would create current. If he stopped, it wouldn't. Okay, and then he also did some experiments where he would have a solenoid, a wire wrapped around an iron core, and then he would bring a powerful magnet and he would touch the iron core. Okay, and if he did that, then this iron core would become magnetized. And he found that while it was becoming magnetized, he could induce current. Okay, all right, so you would touch it, the bar would become magnetized. While it was becoming magnetized, current would flow. Once it was fully magnetized, the current would stop. He could remove the strong magnet. This would eventually lose its magnetism, and in the process of losing its magnetism, current would flow again until it was fully demagnetized, and then the current would stop. So he found those three things, and with those three things he came up with the law of electromagnetic induction. And here's the law. I'm going to read it to you. You can play this back as often as you want in order to get it. But here it is. It's a fairly simple law. And again, it's Faraday's law of electromagnetic induction. He said, whenever the magnetic field in the region of a conductor is moving or changing in magnitude, electrons are induced to flow through the conductor. Okay, so whenever the magnetic field is moving or changing in the presence of a conductor, electrons are induced to flow through the conductor. All right, so in this way we can, without a source, without a battery, we can create current, because current simply is moving electrons. All right, so that's inducing a current, creating a current without a source, a battery, a cell, those kinds of things. All right. We're going to go over to the other board. Faraday came up with a design where he could induce current. We're going to take a look at that quickly. And we're going to look at how the strength of the current is. And we're going to leave it at that for today. And there actually won't be an assignment today. And then tomorrow we're going to look at the direction. And then in the direction there will be a bit of an assignment. And then what we're getting to, again, as I said, we're getting is to transformers and generators. And again, we're going to finish this up this week, so by Wednesday we'll have it all done. And Thursday will be a bit of a review day, and then Friday is going to be your test. But let's go over and talk about Faraday's ring. So, on this board I've drawn what is called Faraday's ring. Now, Faraday's ring is a soft iron core, okay? A soft iron loop, hole in the middle, and this is soft iron. Now, soft iron is just a term used for a type of iron that can be magnetized, all right? Temporarily magnetized. So when you bring a magnet to it, touch it, it gets magnetized for a bit. When you remove that magnet, then it demagnetizes. And so what Faraday did was he took the soft iron ring, and on one side he had a source of electricity. So whether this was a battery of some kind, this is what he did. He set it up here, and then he could create, he could not create, but he could have a current in this circuit, right? This very simple circuit. He has a switch here to turn it on and off. There's no resistors in this, just the wire itself. And so the wire would go, it would wrap around one side of the soft iron ring and come back to the source. All right, and so then he could turn on and off the current on this side. So this is called the primary coil, or the primary circuit, okay? And then on the other side, he had a circuit, again, a wire being coiled around this side and then leaving, and it's connected to anything. Now this circle with a G in it stands for a galvanometer. A galvanometer is simply an ammeter that also measures direction. So if you've ever seen an ammeter, you probably haven't. Most of them are digital nowadays anyway, but we have some here at the school that are still analog, and they have a pin and needle that shows. And on an ammeter, it starts at 0 down here and then measures current. On a galvanometer, 0 is in the middle, and then it measures current one way or the other way depending on which direction the current is going. So that's all this G stands for. This could be anything. We could put a light bulb here. We could put any electrical appliance or anything we want on this circuit because all we're doing right now is showing that current will show up here. So what Faraday did was he would close the switch. Current would flow through the wire. As current flowed through this solenoid, it would create a magnetic field, much like a bar magnet. That magnetic field would magnetize the iron core. Based on what he found in his law of electromagnetic induction, while this core on this side was being magnetized, current would be induced to flow here. Okay? Eventually, it would become fully magnetized and the current would stop. He would then open this switch, which would stop the current, which would stop the magnetic field from being produced here. This iron core would slowly become demagnetized. While it was being demagnetized, again, current would flow through the circuit on this side. Okay? And if he could do this fast enough, if he could open and close this switch fast enough, he could create a current over here that could run something. Now, because of magnetizing and demagnetizing, there's a difference in the direction of the current flows. And so on this side, we would get an alternating current, which is what all of our homes are run off, as an alternating current using this property. All right? And different types of iron will magnetize and demagnetize faster or slower. And so if you get something that can be done pretty quickly, we can have alternating current that lights our homes with what appears to be a steady stream of electricity, right? But it's really alternating. So really, the lights in this classroom, most of these lights are on 60 hertz, which means that the current is changing 60 times a second, right? And we don't notice that, right? We don't notice that because when it goes through zero, for that brief instant, there would be no electricity at that zero, no current flowing through the current of the circuit at that instant. But again, that happens so fast, 60 times a second, the lights don't have a chance to come off and go back on, they just stay on. All right, so Faraday set this up, close the circuit, magnetized, while being magnetized, current. Open it, starts demagnetizing, while it's demagnetizing, current flows here. All right, close it again, magnetizes, while magnetizing, current. Open switch, demagnetize, current flows. All right, so that's the basis of it. And again, if we can, instead of having a switch that opens up and down, if we could have something else that would create a current that sort of goes on and off, okay, then it could be more efficient than having a switch, right? And so in Manitoba, we use water to do it, right? To spin a generator, and a generator produces this side, and then inside of our transformers and the substations around, you see them all over the place, and there's boxes or circles, little containers on the hydro poles, those are transformers as well. And they, inside a transformer, is essentially this, and that allows us to create a current on the other side. Now, there's obviously a magnitude of the current as well, right? The number of amps that can be produced. And so through Faraday's experimentation, he found that there were three things that affected the induced current, the magnitude of the induced current. Okay, the number of turns on the coil. Okay, so the number of turns anywhere in here. Okay, so if we created more turns here, we would create a stronger magnetic field, which would create a stronger current over here. And same thing, the more turns we had here would create more current. Okay, it's a direct relationship between the number of turns and the amount of current that is being induced. Okay, he also figured out that the rate of change or the rate of motion of the inducing magnetic field. So again, how fast can this be magnetized and demagnetized would affect how much current could be produced on that side. And also finally the strength of the magnetic field. So how strong of a magnetic field can I create here would then affect how much current is produced over there. Okay, these are all direct proportions. More turns, more current, a faster rate of change, more current, stronger magnetic field, more current. All right, so that's the properties. Those are the things that we need to know. So I hope you've watched this video fairly carefully. The biggest things are knowing your solenoid right-hand rule. Okay, where is that North Pole? That's going to become very important tomorrow. And this concept of Faraday's ring is going to become very important as well. All right, that's it for today. Have a great day. We'll see you tomorrow.